Orthodontic archwires. So in the previous presentation, we discussed about the classification of orthodontic archwires, the historical perspective, gold and gold alloys and stainless steel alloys, as well as cobalt, chromium and nickel alloys. Moving ahead in today's presentation, let's start with nickel titanium alloys. Nickel titanium alloy was marketed as Nitinol by the Unitec Corporation. It is quite useful in clinical orthodontics because of its exceptional springiness. The generic name Nitinol, which is applicable to this group of nickel titanium alloy, originates from nickel, titanium, and the abbreviation NOL, which stands for Naval Ordinance Laboratory. It was invented by William R. Buchler and introduced in orthodontics by Andersen in 1971. Its main use is during the initial orthodontic alignment, where it can be used to apply a light force over a large range of activations. Discussing the advantages and disadvantages of nickel titanium alloys. The main advantage of nickel titanium alloys is its superelasticity and shape memory. So now let's try to understand what that is. Shape memory is one of the remarkable properties of nickel titanium alloys. It refers to the ability of the material to remember its original shape after being plastically deformed. So there are two major nickel titanium phases in the nickel titanium wires. Martensitic phase, which has a distorted monoclinic, triclinic or hexagonal structure and forms at low temperatures and high stresses. And the austenitic phase, which has the ordered body-centered cubic structure, which occurs at higher temperatures and low stresses. The shape memory characteristics of nickel titanium alloys are associated with a reversible transformation between the austenitic and martensitic phases. The martensitic phase forms from the austenitic phase over a certain transformation temperature range or when the stress is increased above some appropriate levels. The difference in the temperature ranges for the forward transformation from the martensitic phase to the austenitic phase and for the reverse transformation is termed hysteresis. In order for a nickel titanium archwire to possess shape memory, the transformation of the phase must be completed at the temperature of the oral environment. And a key point to be noted in this case is that the shape is set in the austenite form. The next main property of nickel titanium alloys is its superelasticity. So it's basically transition to martensitic in response to stress. So in our previous presentation, we have discussed about mechanical properties of orthodontic archwires, where we looked at the stress strain graph. So till the proportional limit, stress is directly proportional to strain. Superelasticity refers to a condition where stress remains constant, but the strain gradually increases. So in this phase, the wire can be elastically deformed to a great extent without increasing much force. So superelasticity basically refers to the very large reversible strains that certain nickel titanium wires can withstand due to the martensite to austenitic phase transition. So due to this superelasticity, it leads to a loading and unloading graph of nickel titanium alloys, especially the alpha nickel titanium. The loading graph is termed as the pseudoplastic stage, whereas the unloaded graph corresponds to the pseudoelastic stage. The different loading and unloading curves produce the even more remarkable effect that the force delivered by an alpha nickel titanium wire can be changed during clinical use merely by releasing and retying it. So you can see the loading and the unloading curves. So point to be noted here is that superelasticity exists only when both phases of metal are present. So both the austenite and martensite form should be present. The other advantages of nickel titanium alloys are its high spring back and working range. So we discussed about spring back in the previous presentation. It has low stiffness. Two new superelastic nickel titanium wires have also been introduced, namely Chinese nickel titanium and Japanese nickel titanium. The disadvantages of nickel titanium alloys are that it is resistant to taking bends, form helices or loops, and it cannot be soldered or welded. Another variant of nickel titanium alloys is the copper nickel titanium or thermal alpha nickel titanium wires, which was introduced by Rohit Sachdeva, and Suichi Miyaski in 1994. It is composed of copper, about 5 to 6%, which is added to increase the strength, to reduce hysteresis, and reduce phase transition temperature. Chromium is added in a concentration of 0.2 to 0.5% to return the TTR close to oral temperature. TTR, that is the transition temperature range at which the phase transition occurs. So in these alpha nickel titanium wires, phase transition occurs by stress application as well as by thermal induction. So the changes occur at oral temperature. So depending on the AF temperature, that is the austenite finish temperature, copper nickel titanium can be classified into 4 types. Type 1 has an austenite finish temperature of 15 degrees centigrade. It is not used for clinical applications due to its high force level. Type 2 has an austenite finish temperature of 27 degrees centigrade, which generates heavy force than type 3 and 4 wires. So it is best used in patients with average or high pain threshold, and it is used in patients in whom rapid tooth movement is required and patients with normal periodontal health. Type 3 has an austenite finish temperature of 35 degrees centigrade and generates mid-range of force. It is best used in periodontally compromised patients where relatively low forces are required. And finally, type 4, which has an austenite finish temperature of 40 degrees centigrade and generates tooth moving forces when mouth temperature exceeds 40 degrees centigrade. So these wires are best suited in patients who are sensitive to pain with periodontally compromised dentition. So this is the loading graph of copper nickel titanium wires. So it exhibits a small drop in unloading force than is true with other nickel titanium alloys. Moving on to beta titanium. The beta titanium orthodontic alloy is also called as T.M.A, which represents titanium molybdenum alloy, is marketed by the Ormco Corporation. The wire has the potential for delivering lower biomechanical forces compared to stainless steel and cobalt chromium nickel alloy. It was introduced by Jon Goldberg and C. Burstone about 2 decades ago in Orthodontics. Its advantages are: it offers a highly desirable combination of strength, springiness, and formability. Excellent choice for auxiliary springs and for intermediate and finishing arch wires, especially rectangular wires for the late stages of edgewise treatment. Another clinical advantage of the alloy is that it possesses true weldability. It also has excellent corrosion resistance due to the presence of thin adherent passivating surface layer of titanium oxide. And another important benefit of it is the absence of nickel. The disadvantages are that heat treatment is not recommended. Beta titanium wires are generally the most expensive of the orthodontic wire alloys, and T.M.A wires have high surface roughness. So this is just a comparison of the various orthodontic arch wires that we discussed: stainless steel, nickel titanium, beta titanium, and cobalt chrome nickel alloys. In terms of spring back, nickel titanium has the highest spring back. Stiffness wise, stainless steel has highest values in stiffness. Formability wise, except for nickel titanium, rest have a good formability. Resilience wise, beta titanium has adequate resilience. Biocompatibility, nickel titanium, because of the presence of nickel, can have nickel allergy. And joinability wise, stainless steel and cobalt chromium nickel have good joinability. Next, moving on to Optiflex arch wires. These were developed by M.F. Talass in 1992, and they are made up of clear optical fiber. They are composed of a silicon dioxide core which provides the force or resilience to the wire. The silicon resin forms the middle layer, which adds strength to the wire and also protects the core from moisture. The outer nylon layer makes the wire taint resistant and also prevents it from damage. These wires provide light continuous forces and are used during the initial aligning phase of orthodontic treatment. To prevent permanent deformations, sharp bends should be avoided during ligation to brackets. They are available in round as well as rectangular cross sections. So the advantages being it is highly aesthetic and highly resilient, and the disadvantages, as mentioned, that it cannot accept a sharp bend. And lastly, multi-stranded arch wires. They are made up of several thinner wires, either twisted or coaxial. So to increase the strength and to decrease the stiffness of the wire, they are braided or twisted together by the manufacturer. So this increases the flexibility so that it can sustain large elastic deflection in bending. The different types are twisted, coaxial, which has a central core wire with about 5 outer wires wrapped around it. And there is the straight woven variety as well. The advantages are it has increased flexibility and can sustain large deflections. It applies lower forces when deflected and thus has a good working range. So it's basically used in situations wherein light continuous forces have to be applied. So with this, we complete the topic of orthodontic arch wires. So over the years, several alloys like cobalt chromium, nickel titanium, beta titanium, and multi-stranded stainless steel wires with desirable properties have been adopted in orthodontics. In this vast ocean of different orthodontic alloys available, it becomes very difficult for an orthodontist to select a proper wire with the required properties. Therefore, the clinician must be thoroughly conversant with the various mechanical properties of the wires and their clinical applications. I hope you have liked this presentation. Please do like, share, comment, and subscribe to the channel. Thank you.